All right, welcome to the next video in our statistics series here. We are looking at section 12.2. We're still looking at two populations, and in this case, well, not necessarily two populations. Two new tests that are very similar. And what we're actually doing is we're comparing multiple populations. The test for independence is going to be comparing two different variables and wondering if two different variables are independent. And the homogeneity of proportions is, say, we have multiple populations, and we're wondering if all the proportions are the same, the proportions of success or whatever we're looking at are all the same, or if maybe one of them is, at least one of them is different. So let's start with the first one here, the test for independence. So I've got some theoretical results. This isn't actual survey results, but say we're looking at these survey results from some students. We ask whether they enjoy math, and so we have the student's sex, and then we have whether they agree or disagree in their rating on this. And so then the question here is, all right, well, these are the actual survey results. If they were independent, if the two variables were independent, how many would we expect in each cell? Well, let's think about what we know about independence. If they're independent, the probability of male and strongly agree, which is up here, that probability would be the product of the two probabilities, probability of male times the probability of strongly agree. Well, we have some numbers here. We know the total that strongly agree, and we know the total that are male. So we could find, in theory, the probability that a student is male, and we could find the probability that a student strongly agrees, and we could multiply those. And we could say, well, in theory, the probability that a student is male and strongly agrees is about 0.09. And so then the number that are in there should be 9% of 82, or about 7. And so we can extend this and kind of figure out, well, how many would we expect in each of these cells? So let's be a little more detailed here. Instead of, we're going to try to see if we can come up with a more condensed formula for a way to find how many to expect. So that 0.09, that came from 21 out of 82 times 30 out of 82. And you'll notice that there are 82s here that can simplify. And so we really could just say 21 times 30 out of 82. And I don't know why I said 7 on the other side. It should have been 8 or 7.7. And so the essence here is we get this formula that the expected frequency for each cell is the column total times the row total. The reason is you end up with column total out of total times row total out of total times total, and one of the totals in the denominator simplifies, and I don't know why I thought that would be simpler saying it that way. Okay. Like everything here, we're going to use StatCrunch to calculate these things, but it's good to understand where that is coming from. So let's look at the table here and see if we can figure this out. So for each one, we're going to take the column total times the row total and divide by the 82. So if we scroll through here, the first one, yeah, 7.7. So 21 times 30 out of 82, 21 times 52 out of 82. And if we keep going through here, keep doing all that multiplication, we get this is what we would expect. So if they were independent, this is how many we would expect in each cell. So one nice way to check this is we should be able to add, and we should still get the totals. So if we add those two together, all of these totals are equal, and we can add across as well, kind of confirming our suspicions about what those totals should be equal to. All right, so what are we going to do with these? Well, we need a new test. You'll notice this is very similar to the goodness of fit test from the last video. This is a chi-squared again, and again it has the observed minus the expected squared over the expected. This follows a chi-squared distribution. Here's the degrees of freedom. It's 1 less than the number of rows times 1 less than the number of columns. And again, just like the goodness of fit, all the expected frequencies have to be at least 1, and no more than 20% should be less than 5. And if we have to, we can combine categories. So we have a test for independence. The key here, this is a usual hypothesis test, but the key here is that the null hypothesis, we're assuming until proven otherwise that they are independent. And you're trying to prove that they're not independent. You're trying to prove that there's some relationship. So if they're independent, the observed and expected should be very similar. if they're independent, then all those probabilities and the number that we would expect in there should be the same as what's actually in there. So the chi-squared value will be very small and it'll have a low probability, a low p-value. So again, just like the goodness of fit test, this is always a right-tailed test. So in StatCrunch, we're going to use, this is actually, there's no test for independence tab. It's under the contingency table, and then there's a test that you can do in there, and we'll talk about how to do that. So here are our observed categories, and this is our expected. If we look at them together, what we would do here if we were doing this by hand is we would take observed minus expected squared over expected plus observed minus expected squared over expected plus observed minus expected squared over expected, etc. So we're going to use StatCrunch to do that, and so our null hypothesis here is that they're independent. The student's sex and their enjoyment of math is independent, and the alternative is that they are not independent. There's some relationship there. Alpha here, did we say? Oh, I don't know if we did. I think we did. We'll use 0.05. And then we have the test statistic and p-value. So let's see if we can get to StatCrunch. All right, so I have the data in the example file here. So we have, what we're going to do is we're going to go stat tables, contingency table with summary. And the columns that I want are the strongly agree. I'm going to hit the control all the way down to strongly disagree. And then row labels are in under the gender. And then I think that's it. We can display the expected count if we want. There's no need to do that. And we want the chi-squared test for independence. You'll notice there are some other ones here, but a lot of these are 2x2 only. And so hit compute. And here you'll notice all these expected values are just what we had found. And then there's this chi-squared value and a p-value. So if we go in here, there's our output. We have our test statistic is this chi-squared 2.42 and a p-value. You might notice on the very bottom here it says, uh-oh, over 20% of the cells have an expected count less than 5. This value is suspect. So the issue here is these over on the right, there's 10 cells here and 3 of them are less than 5. So 30% are less than 5. That's no good. So what we can do is we can just combine those together. So combine the 2 and the 1 to get 3. Combine the 2.9 and 2.2 to get 5.1, and similarly. So we're kind of group those together into one category. So if I go back into StatCrunch, I'm going to just call this degree or strongly disagree. So I'm going to change this to 3 and change this to 11. And so then if we do summary stats, tables, contingency, and we have summary again. So now we're going to go strongly agree, neutral, and then this combined category. Again, row labels are in gender. We can do the expected count if we want, and we'll hit compute. And now no red flag here because none of our expected values, in fact, are less than 5. All of our 8 expected values are at least 5. Notice it didn't really change the p-value that much. It's still a really high p-value, so it still didn't change the outcome of the test. But we'll use that one. It's a little more dependable, but definitely do not reject the null hypothesis. So we don't have enough evidence to say that they're dependent. We don't have enough evidence to say they're not independent. All right, so that is a test for independence. The next one we have is called a homogeneity of proportions. Homogeneous, when things are homogeneous, they're all the same. So we're wondering here if all the proportions are the same. So what I have are some sample data here from, say we have some various high schools, and we're wondering if students from those various high schools all perform equally at the community college. So we have 4 different districts and the success rates from students in those districts and the number of students from those districts. And you can see these are all they're all kind of in the same interval. 0.62 is kind of small, but is it statistically different? Well, do I check it? Is it statistically different from 0.67 or 0.73 or 0.71? We'd have to check all of those differences. So what we're going to do is we're going to do a test where we're going to assume they're all the same and try to look for evidence that one of them is different, or at least one is different. So this test is essentially going to be the same as the test for independence. We're going to get the number of successes and failures and then try to determine whether success is independent of district. So the way we're going to get, here's the null hypothesis, is we assume they're all equal, and the alternative is at least one is different from the others. So what we're going to do is we are going to do, well, if 67% of them were successful, we'll just multiply to get the number of successes, and if we do the complement, that'll give us the number of failures. Same thing for all of these. So then we have a number of successes and failures for each district. So then we'll make a new table that has successes and failures for each district, and now we're just basically going to do a test for independence and see if the success is independent of the district. So null and alternative hypothesis, the null is that all the proportions that are successful here are the same. The alternative is that at least one is different. And then we've got our usual things here. So let's go over to StatCrunch, and I think I have those numbers. I put them in here. Here they are. And so again, we'll just do stat tables, contingency with summary, and now we're going to do success, failure, and what am I looking for? Row variables are in district, and we can do expected counts. We don't really need it. We can do compute here. Let's take off the expected count. That just gets a little cluttered. Oh, I can't take it off, can I? Yeah. All right. So there we go. And we can see our chi-squared is pretty small. Our p-value is very large. So even though those percentages were a little bit different, there does not seem to be enough evidence to say that the proportions are not the same. So the key here is converting those proportions to successes and failures and then doing a test for independence. So you can see very similar to seemingly different ideas. Are these two variables independent, and then are these proportions all the same? But really it comes down to the same test. And so that is it from section 12.2.